further trigonometry, addition and double angle formulae. So we're going to be looking at what the addition and double angle formulae are and how we can use them to solve problems. So here's our unit circle, and here's an angle A. Using right angle trigonometry, we've looked at this a few times before, so O to N is cos A because it's adjacent over hypotenuse, and PN or NP is sine A, opposite over hypotenuse. So my coordinates of P are cos A sine A. Now if I choose another point Q, still on my unit circle, but with a larger angle, which I'll call B this time, then my hypotenuse is still 1, and OM is cos B, and MQ is sine B. So the coordinates of point Q are cos B sine B. Now, if I join P to Q and I zoom in on this line segment here, I can draw a right-angled triangle, and my base is just the difference in the x coordinates, and my height is just the difference in the y coordinates. So my base is cos A minus cos B, and sine A minus sine B. And we just take their positive version there because we're thinking about lengths. And so PQ squared using Pythagoras is cos A minus cos B squared plus sine A minus sine B all squared. Now I can expand those brackets. So this is cos A minus cos B all squared, and this is sine A minus sine B all squared. Now I can group up some of my terms to make it simpler. I have a cos squared A and a sine squared A. So I'm going to group those together, similarly with cos squared B and sine squared B. Hopefully you can see what I'm going to do there. They're both equal to 1, each of these brackets. So I can simplify to say PQ squared equals 2 minus 2 times cos A cos B plus sine A sine B. Now, I can also look at this triangle OPQ. The angle here is B minus A. The angle B minus the angle A. Both of the side lengths for OQ and OP are 1 because they're on the unit circle. They're the radii of the unit circle. And so, using my cosine rule, I can substitute in my values to get PQ squared equals 1 squared plus 1 squared minus 2 times 1 cos B minus A. Now, because cos of an angle is equal to cos of a negative angle, I'm just going to rewrite cos B minus A as cos A minus B. Now, I have two expressions that PQ squared is equal to, so I can set them equal to each other. Now, I can subtract 2 from both sides and divide both sides by negative 2. And I get this statement. This is an identity, it is always true. And using the steps, similar steps to the ones I've just gone through, I can also get this identity for cos A plus B. And we can also have do something similar for sine A plus B and sine A minus B. So let's use those to find identities for tan of A plus B, tan A minus B. So from previous lessons, we know that tan of an angle is equal or identical to sine of the angle divided by cos of the angle. So I can take my identities for sine A plus B and cos A plus B. Now, here's a sneaky little trick. I can divide everything, my whole numerator and my whole denominator, by cos A cos B. Gives me this delightful expression, but then we can see that there's lots of things that cancel out here. This was what I divided everything by, and obviously dividing by cos A cos B over cos A cos B is just the same as dividing by 1. So cos B over cos B cancel. Cos A over cos A cancel, they're just equal to 1. And cos A cos B over cos A cos B cancels, that's equal to 1 as well. So I'm left with sine A over cos A, which gives me tan A, sine B over cos B, tan B, and sine A sine B over cos A cos B, so that's just tan A tan B. And I can do the same thing for subtracting as well. Now, this is how you get given the identities on your formula sheet. So notice we've got sine A plus or minus B is identical to sine A cos B plus or minus cos A sine B. So with the sine one, sine and cos go together, and then you switch around which one's A and which one's B. For cos of A plus or minus B, this is identical to cos A cos B, so both coses, minus or plus sine A sine B. So that means if you have plus, then you use minus in the identity. If you have minus, then you use plus in the identity. And same for tan. So tan, you've got two different situations. The numerator is the same as whatever you're using in your tan A plus B. This would be tan A plus tan B, but then the denominator is the opposite one. So you don't need to remember them, but it's just important to notice the differences between them. Okay, so I've just written this as two separate ones so you can see what that means. Okay, so let's have a look at using them. Find an exact value of sine 15 degrees. At the moment, we don't know that, but we do know some exact values. We know 30, we know 45, we know 60, and 0 and 90. And then things past the pi, oh, we're doing degrees, things past 90 degrees as well. So can we use any of the ones that we know to make 15? Well, yes, we can. So we're going to be looking at sine, and we're going to have a look at the subtraction one. Why are we looking at the subtraction one? Because 45 minus 30 gives us 15. So I can just substitute 40 and 30 in for A and B. Now I know what each of those are, so I can write those out individually. Sine 45 is root 2 on 2. Cos 30, root 3 on 2, and so on. Then I can simplify these, multiply them together, and then I have the same denominator, so I can write that as a single fraction. Pause the video now while you have a go at questions 1 to 6. So we can express sine 2a cos 2a tan 2a in terms of the angle A using the double angle formulae. We're going to have a look at where the double angle formulae come from. So here's my sine addition formula. I can replace the B with an A on both sides. Now I can simplify. So sine 2a, and I've just got sine A cos A sine A, which obviously is the same. So I can write that as 2 sine A cos A. And then different ways that I can manipulate this to make it useful for me. I could divide it by 2, so half sine 2a equals sine A cos A. I could put 4a in instead of 2a, in which case each of these a's would become 2a. I could multiply it by 3. I could have a specific angle that 2a is equal to. Let's have a look at cos then. So same as before, we'll replace b with a. Now I've got cos A, I can write that as cos squared A. Sin A, I can write that as sine squared A. So this is an identity. What we can do here, because we know other identities that involve cos squared of an angle and sine squared of an angle, is we can create some new identities. If I replace cos squared A with 1 minus sine squared A, I can simplify that. And if I replace sine squared A with 1 minus cos squared A, get this. So there's 3 different identities for cos 2A. Finally, with tan, replace the B with an A, simplify, and like I showed you with sine, we can do different things. I could divide it by 2. I can substitute in a specific value for an angle. I could double it. Or I could say that 2A is equal to A, in which case my A's would become A over 2. Whatever this angle is, it's half of this one here. So now you've got those other identities, you can finish off the exercise 14D. Thank you. Oh, here's question 12, sorry.